The presentation will be myself, just some work. My name is Quoc-Bao Bui. I received my PhD in 2008 at ENTPE, Lyon, France. From 2008 to 2011, I continue at ENTPE as a postdoc. From 2011 to 2016, I work as associate professor at Polytech Annecy-Chambery, University, Savoie Mont-Blanc, France. Since 2016, I have joined Ton Duc Thang University, Vietnam, as associate professor. My research interests cover non-conventional material such as soil-based material, recycled material, and structural analysis. I have recently been involved in this activity related to chemical activation, especially alkaline-activated material, and I have published about 60 articles in international journals. So I will do the share screen. Yeah, just before that, I will do okay. Okay, so my presentation has the title Recycling in Construction Material Case Study with the participation from TDTU team, Mr. Lê Hoài Bảo, PhD student, Dr. Lê Đức Hiển, Dr. Trần Minh Tung, and Dr. Phan Thu Anh Vũ. I will try to be short, so my presentation has three sessions. First, the introduction, then the case study with the Geopolymer recycled aggregate concrete and Geopolymer Adobes, and finally the conclusion. For the introduction, fly ash and bottom ash in Vietnam and in some other country on the world, the thermal power plant use charbon, which generate a lot of waste, the bottom ash and fly ash, and every year about 15 million tons generated in Vietnam, about 65% in fly ash and 25% bottom ash. So we will not have enough storage space in thermal power plant site for bottom ash and fly ash. In many cases, fly ash can be used for cement industry, but in numerous thermal power plants, the fly ash separation phase is not included. So the fly ash generated do not have satisfying quality for cement production, and the post-treatment is expensive. So the bottom ash and fly ash poorly become waste, which give a serious environmental problem. On the other hand, in Vietnam, the Vietnamese government willingness try to reduce and replace clay burnt brick by more green material, and in general, the unburnt brick are often proposed, but the unburnt brick have several difficulties due to the economical, the traditional, the environmental problem. For example, a high cement amount is usually used in unburnt brick. For example, in some cases that can reach 25% by weight. Thus increase the cost and the carbon footprint. another demand, that is the recycling demand. For example, for the total inert waste, the concrete waste is about 10% of the total inert waste, but the soil is also about 50% of the inert waste. And we will try to recycle the concrete, but in general, the soil is not recycled for construction material, and this is a possibility to be explored. So Professor Jean-Claude Morin has presented some approaches on that way. Here I present some different strategy that we have investigated. The first one is the using fly and bottom ashes for construction material. The second is using recycled aggregate for concrete. The third is the using local soil for construction material production. And the fourth is reduce and replace the cement amount in construction material. Due to the time limited in this presentation, I will present two case studies. The first one is geopolymer recycle aggregate concrete, and the second just a short about the second case, the geopolymer Adobe, a type of unbent bricks. The first one, a geopolymer recycle aggregate concrete, GRAC. First, we obtain the recycled coarse aggregate by crushing and washing from the old concrete. And we have done the characterization on mortar content. For example, that is on this picture, you can see the natural stone and the old mortar bonded on the natural stone. We characterize the absorption, the water absorption, the specific gravity, and the aggregate crushing value ACV. This table presents a summary of different value obtained on the recycled concrete aggregate and on natural aggregate. And you can see from the ACV value, we can extrapolate the compressive strength. For the natural aggregate, we have 70 megapascal, but for recycled concrete aggregate, the value is a half, about 50%. Recycled aggregate has lower quality than natural aggregate due to the old mortar bonded on the original aggregate, and you know the mortar has a lower quality than the concrete. And the second is that there are some degradation of microstructure during recycling procedure. For example, during crushing, that can cause some micro cracking on the aggregate. And we have investigated on different variables. We use the low calcium class F fly ash, and for recycled concrete aggregate, we try with untreated procedure, and we try with treated procedure. We use a natural river sand. And for alkaline-activated by the AAS, we use the sodium hydroxide and natrium silicate with different ratio, AAS on fly ash. And we try with and without superplasticizer, and in our case it is lignosulfonate based superplasticizer. And we try also for the curing temperature. We try a normal ambient curing, and we try a curing with 60 degrees Celsius during one day. we don't want to use high temperature because that consumes a lot of energy. So it's not very interesting in the environmental impact point of view. And because we want to develop some analytical, some empirical model, so we must determine also the geopolymer strength. But we have two types of geopolymer. So the first one is geopolymer based. That means just a geopolymer without sand. And the second one is geopolymer mortar with sand, which is in general used in the standard. So because the geopolymer, we don't have a lot of standards about that, so we try different type. The result, first on the workability of GRAC, you can see for the influence of the ratio alkaline-activated solution on fly ash from 0.4 to 0.5. And in the case of with and without super plasticizer, we can see with the super plasticizer, the slump increase slightly, but that's increased. And we see also when the alkaline-activated solution increase, the slump value increase also. And for the compressive strength with super plasticizer and with different ratio alkaline-activated solution on fly ash, we can see that and for different conditions, current at 60 degrees Celsius and current at ambient condition, we see that with the best ratio between 3 ratio IAS on FA is 0.4 for the case current at 60 degrees Celsius, and also for the case current as ambient. And we will see now the case without super plasticizer, and we see also the ratio 0.4 is relatively the best one. Not always, but in general, this is the best one. And we can compare between the case current at 60 degrees Celsius and current at temperature. We see that, for example, at ambient temperature, the mean compressive strength is about 30 megapascal at 28 days. But for the case of current at 60 degrees Celsius, the mean compressive strength is about 33, 34 megapascal at 28 days, and it is the same tendency, the same trends for the case with super plasticizer. And now some analysis at microscopic scale. First, we can see some development of gels in GRAC. For example, in this, on the left, we see the aggregate and the geopolymer gel development. And we can see also the large size fly ash particle already reacted. On this picture, you see a big circle, a big sphere, which is the big spherical fly ash particle already reacted. And inside of the big spherical fly ash particle, we have some small fly ash particle released. So, but the smaller fly ash particles are still unreacted. And between the fly ash particle, we can see some geopolymer gel developed. And we can see also the correct bonding between the paste and the aggregate. For example, in this picture on the left, we see the aggregate and the paste. You can see the interface is correct. And if we do a zoom about at 5 micrometer, we can see also the geopolymer gel with the tabular form and the aggregate. The result about compressive strength of geopolymer, mortar or paste, as I said, they are not standards on geopolymer, paste or mortar, so we try three types: the paste, the mortar, and the mortar following standards. And we obtain the relationship between the compressive strength and the time for different composition, and we can see that the geopolymer, mortar or paste have higher compressive strength than GRAC. Thus, here we have between 50 to 70 megapascal. So we can say that the lower compressive strength of the GRAC, the concrete, is due to the low quality of the recycled aggregate. Now we try to propose some model for the strength prediction of GRAC, and we based on two classical models for Portland cement concrete. The first one is the Ferret model, in which Kg is Ferret constant depending on aggregate quality. So we must identify Kg for the case of recycled aggregate, because the basic Ferret model was proposed for natural aggregate. The second one, because the Ferret model was proposed for cement concrete, now when we use for geopolymer concrete, we must propose a modified model to take into account geopolymer by using a coefficient KB, K binder. So we don't use only cement, but we use binder. The second model is the Delara model, and we must identify the value P and Q for GRAC instead of P and Q for natural aggregate and cement concrete. The result for the modified Ferret model, first we try as 28 days with different KB value and Kg value, and the horizontal line is the experimental result for the ambient curing and curing with heating also. And we do a optimizing procedure to identify KB and Kg, and we can say that Kg about 3 and KB about 0.6 is the best, due to different value at different time. For example, on this figure, the variation of compressive strength on the time obtained from the model, the modified Ferret model, with heating and with ambient, and the points are the experimental value. So we can see that the model can predict relatively well for 28 days, 14 days, and 7th day. For the 3 days. For 7 days, the result is a little different. The same for the Lara model. We have done the same approach to identify the value of P and Q. And here we can obtain a similar trend. We obtain the better result. The numerical line are closer to the experimental value. Only at the 7 days, the value are more different. There are more difference between experimental value and numerical value. So due to the limited time, the second study on the Adobe technique. Adobe technique, that's the brick compressed by hand. And we use in situ soil of a construction site. We try geopolymer from 6 to 20%. We obtain the dry density of the brick from 1.8 to 3.1. And we obtain the mean compressive strength from 6 to 35 megapascal. This is too much for brick. And the absorption is about 5%. And we observe that the curing acidity at 90 degrees Celsius during 1 day can have to increase the compressive strength about 30%. So the value satisfying following American standards on absorption and compressive strength, that is satisfying for load-bearing brick. And in general, maybe we need only for non-load-bearing brick. So the optimization may be continue to reduce the minor amount to reduce the cost of the brick, at the same time economical cost and environmental cost. So we have some conclusion, but I think I can stop my presentation here. Thank you for your attention. So.